Welcome to the Blueprint Room. I am your chief architect, and today we are taking on an absolutely critical construction project. We're tackling what is arguably one of the most structurally demanding challenges in the entire Cambridge AS and A-level Mathematics 9709 syllabus. I'm talking about complex numbers and loci and Argand diagrams. Now, in this explainer, we aren't just looking at math like it's a dusty textbook. No, we are treating it exactly like a high-stakes, high-rise construction site. To pull this off, joining us on the drafting board today are our virtual apprentice builders, Alex and Sam. Now, Alex and Sam are going to help us demonstrate exactly how to build an unshakable mathematical foundation. Our ultimate goal today, we are bridging that massive structural gap between a B grade and an A-star grade, and we're doing it through pure, unadulterated mathematical integrity. So grab your hard hats and let's dive right into this. Now, consider the sheer weight of this quote from a Cambridge senior examiner. Constructing a top-tier exam response is literally exactly like building a high-rise skyscraper. If you want to survive the absolute gale force winds of the Cambridge assessment objectives, you cannot just throw materials at the site and hope they magically stick together. It doesn't work that way. When you're dealing with loci and Argand diagrams, a minor miscalculation in your center coordinates or, a failure to clearly define the shaded region of a half line, well, that means your entire skyscraper comes crashing down under the examiner's red pen. It's a total structural collapse. But don't worry, we are going to ensure that your mathematical building stands tall, proud, and fully 100% compliant with the marking scheme.
To achieve that level of structural perfection, we are going to follow strict, non-negotiable architectural phases today. First up, we'll lay down the core principles. Second, we'll get into the technical methodology. Third, we are going to run a mandatory mid-build inspection. And finally, we'll finish up with a viewer stress test. Okay, entering Phase 1, core principles. Let's isolate the foundational building regulations enforced by the Cambridge examiners. So what is really fascinating here is the core conflict between two totally different building styles. Cambridge strictly demands transferable knowledge. That means your understanding absolutely must hold up in high-stress, completely unfamiliar contexts. Let's look at our first apprentice builder, Alex. Now, Alex is a hard worker, but Alex wants to just stack raw, disconnected facts. He's pouring these incredibly heavy bricks into the foundation by simply memorizing things like, okay, the modulus of z equals 1 is always a circle. That is what we call superficial breadth. And let me tell you, the Cambridge framework entirely rejects this. It prioritizes load-bearing analytical depth instead. Think about it. A skyscraper doesn't stand up just because you dumped a million disorganized bricks on an empty lot, right? It stands because a few strategically placed, highly engineered steel columns carry the actual weight. In pure math, those steel columns mean understanding exactly why the modulus creates a locus of points equidistant from a central coordinate. Every single mathematical step must logically support the weight of the step right above it. Otherwise, you're building on sand.
So the absolutely crucial point here is mastering systematic analysis. When you are hit with an equation like the modulus of z minus a equals the modulus of z minus b, systematic analysis requires you to immediately, without hesitation, recognize that you're dealing with a perpendicular bisector. But here's where most people fail. The evidence-based reasoning requires you to mathematically prove the intersection points and properly shade the exact precise region on the Argand plane based on the inequality given. You have to clearly show you're working. You can't just sketch it and hope for the best. Without this conceptual algebra acting as the mortar holding your geometry together, your loci response is just a pile of loose gravel waiting to be swept away. All right, moving into Phase 2, technical methodology. If Phase 1 was pouring our foundation, this is where we actually weld the heavy ironwork. So, let's observe our apprentices Alex and Sam as they attempt a really high-tariff loci intersection problem from a brutal past paper. The grid lines are flashing, the clock is ticking. But wait, I have to step in right here to define the method mark strategy. You see, Builder Sam loves to do half the complex geometry in their head and then jump straight to writing down the Cartesian equation of a circle. Sam basically wants to put up these beautiful shiny glass panels on the 50th floor without actually installing the procedural steel frame first. You literally cannot do that. If you skip showing the complex algebra conversion steps, the actual structural framing, you lose the method marks. The examiner specifically awards points for the procedural process. You have to show the framework, every single bolt and beam of it, or your mathematical building will be condemned on the spot. This debate between Alex and Sam brilliantly illustrates the three critical steps of data interpretation. Step 1 is extracting algebraic data. This means identifying the exact complex constraints from the raw inequalities given in the prompt.
Step 2 is interpreting relationships, which means finding exactly where a circular locus intersects a half line on the Argand diagram. But Step 3 is drawing evidence-based conclusions, and this is where the real heavy lifting math happens. This specifically means taking the time to test a coordinate to see if it actually satisfies the inequality before you commit to shading the region. Right now, I'm making Alex and Sam tear down their whole paragraph skeleton and rewrite their procedure live. They are now properly testing a point, like the origin, and rigorously evaluating if it holds true under the given constraints. And that, my friends, is how you weld a perfect, unshakable structure.
Now, as we build higher into the upper echelons of the marking bands, we need what we call comparative analysis rivets. In Pure Math 3, when the syllabus talks about comparing approaches, it usually means looking at the intersections of multiple loci. For instance, when you have a circular locus intersecting a perpendicular bisector, you absolutely must compare their boundary conditions. You have to logically link your geometric findings to your algebraic equations to find the one single valid sheeted region that satisfies both inequalities at the exact same time. And you have to support this comparison with concrete, undeniable mathematical evidence, proving those final bounded coordinates. Without these mathematical rivets, your entire solution will just shear off during the examiner's stress test.
And all of this structural work brings us to the ultimate goal, reaching the evaluative penthouse level. Think of it like this. The lower, descriptive floors of a building simply state what the locus is. The middle, analytical floors calculate where it is. But the top-scoring candidates, they reach the evaluative level by actively questioning their own work and fully understanding the geometric implications of the algebra they just performed. They don't just calculate blindly like a machine. They evaluate if their geometric sketch perfectly matches their algebraic solution. For example, when Sam suggests a purely geometric approach to finding a tangent, Alex wisely argues for evaluating the algebraic alternative to double-check their intersection coordinates. That critical, self-correcting algebraic check, that is exactly what earns you the A-star certificate of occupancy.
Okay, moving right along to Phase 3, the mid-build inspection.
Whoa, stop the cranes, hold everything. Right before we pour the final concrete on our mathematical framework, we need to make sure your own construction line is actually reinforced. Take a second to subscribe to Ace the Exams right now, whether you are laying down a solid IGCSE foundation or setting up a towering A-level skyscraper. This explainer series is your primary support grid. Click subscribe, turn on those notifications, and lock it in. All right, back on the site. I'm looking at our digital model, and it is swaying dangerously in the wind. We've hit a major roadblock. I have to step in and ask a vital question. Where do most structural failures actually occur during the examiner's stress test? To answer this, we have to consult the ultimate building inspection documents. I'm pulling up the official Cambridge Principal Examiner reports for 9709 to reveal exactly why student structures collapse on exam day.
These examiner reports issue 3 incredibly severe structural warnings that you cannot ignore. Number 1, students constantly forget proper format in their loci answers. And what does format mean in this context? Well, it means forgetting to use a dashed line for strict inequalities, like strictly less than or greater than, and failing to use a solid line for less than or equal to. It sounds minor, but it's a massive point of failure. Number 2, failing to check presentation. This is like shading the completely wrong side of a perpendicular bisector because you didn't test a coordinate. But number three is just catastrophic. Generic answers without context. This is when you provide a beautifully memorized, flawless geometric proof that has absolutely nothing to do with the specific coordinate scenario presented in the actual question. The structure completely collapses because it isn't linked to the bespoke constraints of the site. When we break down the distribution of these failures, it's quite shocking. Just imagine a breakdown where the absolute largest segment represents those generic context answers. Ignoring the specific context of the given coordinates completely shatters the structural integrity of otherwise perfectly good loci math. It's tragic, really. You can have a brilliant world-class understanding of Argand diagrams, but if you skip your presentation checks and you just completely ignore the specific quadrant constraints the examiner gave you, your building is immediately condemned. 0 marks. So how do we fix a swaying structure before it falls? We use the Peel methodology. Point, evidence, evaluation, and link. Now, you probably thought Peel was just a framework for writing English essays, right? Actually, no. It is the absolute ultimate blueprint for bulletproof mathematical proof. Let's watch our builders actually apply it line by line out loud to replace their failing concrete. First, Alex lays down the point. The locus of the complex number satisfying the equation is a circle.
Then, Sam drops in the evidence beam. Extracting the algebraic data, the center is exactly at point AB with a radius of r, derived straight from the Cartesian conversion. Alex then heavily secures it with evaluation. Evaluating the boundary conditions, the region lies strictly outside the circle, requiring a dashed boundary line because the inequality is strictly greater than. And finally, Sam welds the crucial link. Therefore, linking back to the question's secondary argument constraint, the valid area on the Argand diagram is shaded only in the first quadrant. Boom. Perfect. The mathematical concrete is poured flawlessly. It's not going anywhere.
All right, phase 4, the viewer's stress test. It is time for a live site safety audit, and you are the inspector.
Let's analyze the blueprint matrix. On one side, we have a purely descriptive structure. This is unlinked context, missing procedural algebra, basically an imminent collapse waiting to happen. On the other side, we have the evaluative structure. This uses our PEL methodology, strictly connected math, and verified presentation. Imagine a 60-second visual countdown timer ticking down right now in your exam hall. I challenge you to identify the single core metric needed to pass the examiner inspection here. Have you spotted it? The answer isn't just knowing the formula, it's the connectivity of the math to the specific context. The evaluative structure survives the timer every single time because every coordinate point is mathematically riveted to the specific scenario requested by the examiner. But let's be real. Under the intense, crushing pressure of the exam clock, you need rapid access tools. You can't be pausing to rethink the whole philosophy of architecture. The examiner reports strongly advise having a mental structural checklist. So I want you to think of the acronym CARE. Contextualize the complex problem, apply the proper algebraic format, reason with geometric evidence, and evaluate the final shaded constraints. CARE. By utilizing a quick architectural memory hack like this, you ensure that you literally never leave out a critical calculation step when you're rushing to finish your high-rise before that exam deadline hits absolute zero. All right, team, let's conduct our final blueprint review. These are your absolute core takeaways, the things you cannot forget. Number 1, rely heavily on your method marks. Build the procedural algebra from the ground up. Do not just paste up shiny final answers and hope for the best. Number 2, verify your format and presentation. Double-check your solid lines versus your dashed lines, verify your shading, and ensure you are absolutely in the correct quadrants. Number 3, link everything contextually to the specific coordinates given in the prompt to avoid a complete structural collapse. And remember, to truly solidify these foundations, you must practice past paper questions relentlessly. So, I leave you with this final, critical site inspection question. When the Cambridge examiners apply maximum pressure to your assessment objectives, when the timer is ticking down to the final seconds, will your Argand diagram answers stand tall like a master-crafted skyscraper, or will they collapse entirely under the stress test? The mathematical blueprints are now completely in your hands. I am your chief architect, and I will see you on the construction site in our next explainer. Keep building and keep building strong.